I'm going to go through covalent bonds and dot structures in this video. So we already know that covalent bonds are when you have a sharing of electrons taking place here between atoms. Okay, so if you look here in this picture, these two electrons are being shared between the two different atoms. Covalent bonds are between nonmetals. All right, they're sometimes called molecular compounds because they form molecules. And remember, diatomic molecules are these special atoms that cannot exist by themselves. So O2, H2, so on. They can never be by themselves in nature. So you need to watch for these, especially when doing reactions. So I'm going to walk through the properties of covalent compounds here very quickly. Again, you could pause the video if you need to, go through them a little bit more in depth. But basically, covalent compounds are pretty much the opposite of ionic compounds. So they have low boiling and melting points. Ionic would have higher boiling and melting points. Covalent compounds here are not going to usually conduct electricity. Typically, they're not soluble in water, but covalent do have a wide variety of properties here. So if a covalent compound does dissolve in water, it would not dissociate. Okay, so something like sugar dissolves in water. It's covalent. It's made of carbon, hydrogen, and oxygen, but it's not going to dissociate and it's not going to conduct electricity. Okay, so that's different from ionic. And typically, covalent compounds don't form crystals. Most are actually liquids or gases. But again, there's a wide variety of properties for these covalent. Something like sugar does form crystals. Okay, so these are basically the properties of most covalent compounds. I just wanted to point out the difference here between dissociation and dissolving because this is a big idea. So over here on the left, we have dissociation. This is what takes place when you take an ionic substance and you put it in water. Okay, so remember, dissociation means the substance splits apart into its ions, into the pluses and the minuses. So if you were to take NaCl, table salt, and put it in water, it literally dissolves, but it separates into the individual ions of the sodium and the chlorine. So you get Na plus ions and Cl minus ions floating around in the water. That's dissociation when it splits into the ions. Notice what happens here when something just dissolves. So sugar is a covalent compound. All right, it does not dissociate, but it dissolves. All right, so if you notice here, sugar just gets surrounded by the water. It doesn't split apart. Okay, so each sugar molecule literally gets surrounded by the water, and that's why it dissolves. There's a huge difference here. Okay, ionic compounds will separate into their ions. Covalent compounds, if they dissolve, just basically get surrounded by the water, but they do not split apart into their ions. So if you look here a little closer to compare ionic and covalent compounds, all right, remember ionic compounds are beautifully organized, perfectly arranged, and you can see over here with the covalent with some water, not as perfectly organized, not really that arranged. So there's definitely a difference between the two here, all right, and that's why ionic has specific properties such as, high boiling and melting point, really strong attraction, and covalent, they don't have that strong attraction as much, so they're not as organized. So there are different types of covalent bonding. Okay, so we know covalent bonding is the sharing of electrons, but there's single, double, and triple covalent bonds. All right, a single covalent bond is when you share one pair, double would be two pairs, and triple would be three pairs. Pay attention to the total number of electrons though. All right, one pair is two electrons. All right, so two pairs would be four total electrons. All right, so if you look here, this would be an example of a single covalent bond, just two electrons or one pair is being shared. Here would be an example of a double covalent bond where two pairs or four total are being shared. And here's an example of a triple bond where you're sharing a total of six electrons. Okay, so just remember here though that every atom still wants that magic number of 8 in order to be happy to have that noble gas configuration. So they may only be sharing 4, but each atom itself still wants that magic number of 8 valence electrons. I just wanted to mention real quick about bond length here. So when you have a single, double, or triple bond, as you get more bonds in between these two atoms, the bond length actually gets smaller or gets shorter. Okay, so here in the picture, this would be a single bond. There's just one bond. You can see that in the picture. There's just one line. All right, but then when you add more electrons in between, because remember, a double bond would have more electrons in between the two atoms, it gets shorter. And then when you have a triple bond, there's even more electrons in between the atoms, bringing them even closer together. I mean, it makes sense. The more negatives you get in between the two positives, the more attraction they're going to have for those negatives. So the bond length gets much shorter. But it's also stronger as well. All right. Kind of makes sense that a triple bond would be stronger than a double, which would be stronger than a single, because there's just more bonds in there that you would need to break. This is the difference between single, double, and triple bonds in terms of length and strength. So now we're going to jump into covalent dot structures or molecular dot structures, sometimes called Lewis dot structures here. The basic gist is this is just a visual representation of how these atoms are going to be bonded together. So you can see who's going to be sharing with who, how many electrons they're going to be sharing, how they're organized. Okay, so in ionic, we actually showed the transfer of electrons with the arrows. So this is kind of like that, where we're going to be seeing how these things are bonded together, but we're not going to show arrows because there's not a transfer. We're just going to show the sharing of electrons that would take place. Okay, so we show the valence electrons as dots, and we can see whether a bond is single, double, or triple based on the number of electrons being shared. So that's what we're going to work on here. So I'm going to walk you through the steps here for drawing molecular dot structures. I'll do it really quick. You can reference back to this, but I think actually seeing some examples and using the steps is where it's going to be most helpful. But the first thing you'll do for all of these dot structures, and you'll have to get to a point where you just do these steps. You just know the steps and you just do them every single time. So the first thing we're going to do is figure out the total number of valence electrons that are available from all the different atoms in our molecule. So we have to total them up. And that's the number of dots that we will need to see in our final structure. All right, so that number is important because it's going to tell us if we did it right. All right, so then step two is about talking about here how we organize things. So it says you put any carbons or nitrogen atoms in the center. Okay, so if you don't have carbon or nitrogen in your dot structure, you would put the least electronegative atom in the center. And typically, it's the atom that there's less of in the formula. Okay, so we try to position this so that the atom there's less of would be in the center. We would never put hydrogen in the center unless it was the only element, and we'll see why as we go through this. Then step three says whatever atoms are remaining go around the center atom, and you try to distribute these atoms that are remaining as evenly as possible. And sometimes you might have a couple atoms being your so-called center here, so we got to be careful with this. So now that you have your atoms placed, all right, any atom you put next to your center needs to share at least a pair of electrons with the center. That's covalent bonding. So you would just draw in pairs of electrons here to show the sharing. All right. Once you have the sharing done with your center, then what you do is you have to make each atom in your picture happy by giving them the total number of valence electrons that they want. So you have to add in extra electrons for each atom until they get that magic number. All right, so once every atom is happy, then you total up the number of dots, the total number of valence electrons in your picture, and see if it matches the amount that we totaled up all the way back in step one. If it matches, then you're done. Everybody's happy. You have your maximum number of valence electrons. You're done. All right, but if you're over that number, all right, you would have to add double or triple bonds in, and you would have to remove electrons. All right, if you're under that number, you have to literally just add extra electrons to your center atom. All right, it's very important here that you pay attention to how many electrons, how many valence electrons each atom wants. For example, hydrogen only wants 2 electrons. Hydrogen wants to be like helium. All right, so you would never give hydrogen 8 valence electrons. All right, he only wants 2. So there are some other exceptions here, but this is probably the biggest one, but it doesn't seem like an exception because you just use it so much. I just wanted you to see honk 1, 2, 3, 4 here because sometimes this is helpful when you're doing dot structures and you're not quite sure. It doesn't work all the time. It's not something you're probably even going to reference all the time when you do one of these, but it can be helpful. What this basically says is that certain elements like a specific number of bonds or shared pairs when they are bonding. Okay, so the elements here correspond to the number. All right, so hydrogen likes 1 bond, oxygen likes 2, nitrogen likes 3, and carbon likes 4. Okay, so what that typically means is if you were doing a dot structure with oxygen, oxygen is going to have two shared pairs in some way. Okay, but he still wants 8 valence electrons, so he'll have to have extra electrons on him, but typically he's going to have two bonds. All right, and we'll look at these as we go through some examples. So this is sometimes helpful to remember. It doesn't always work all the time, it doesn't always apply, but it can be helpful in some of these harder dot structures. All right, so now we're going to go through and do some examples. All right, we're going to take all those steps and use them here. Like I said, you got to get to a point where you know the steps and you can just do it. All right, so we're going to do the dot structure here for NH3 to start. Okay, so the first step we need to do is we need to total up the number of valence electrons that are available for us in this molecule. So you literally look at each individual element in the formula, all right, and see how many valence electrons they're bringing here to the molecule. Okay, so the first element in NH3 is nitrogen. So when you look up nitrogen on the periodic table, all right, he's in the 5A column. So each nitrogen has 5 valence electrons. All right, how many nitrogens are in NH3 though? There's just one. So we say essentially it's 5 times 1. Each nitrogen can bring 5 valence electrons, all right, but there's only one nitrogen coming in. Plus, okay, there's also hydrogen in this formula. So how many valence electrons does each hydrogen have? When you look up hydrogen on the table, he's in the 1A. So each hydrogen has 1 valence electron. All right, but how many hydrogens are in your formula? There's 3. So essentially it's 3 times 1. All right, there are no other elements in our formula. Okay, so we total this up. Okay, 5 times 1 is 5, plus 1 times 3 is 3. So it's a total of 8 valence electrons. All right, in our picture when we are done, if we don't have 8 dots, we did this wrong. Okay, if there's more or less than 8, we know it's wrong. Okay, so it's very important that you do this totaling up correctly because it's going to affect your entire dot structure here. Don't always think these numbers need to, be 8 or a multiple of 8 or anything like that. All right, so just total it up and see how many valence electrons you have available. So that's step 1. Step 2 says put any carbons or nitrogens in the center of your picture. All right, so in this formula, we do have a nitrogen. Okay, so the nitrogen will essentially act as our center for this molecule. All right, step 3 then says whatever's left has to go around your center, and you try to place them as evenly as possible. So I have 3 hydrogens left, all right, in the formula. So I'm going to put one kind of on the right, one on the bottom, and one on the left here. Okay, so there'll just be nothing on top. So that's step 3. Whatever is left, you put around your center. Okay, now whoever you put next to your center here, you need to share at least a pair. So each hydrogen is next to your nitrogen, which is your center. All right, so the definition of covalent is they have to share at least a pair. So you would draw in a shared pair of electrons. This is essentially a covalent bond. Between every nitrogen and hydrogen, there is a covalent bond, a single covalent bond, where you're sharing a single pair of electrons. Okay, so now that you shared with your center, all right, the next step is make every element happy. Make each element happy by giving them the number of valence electrons they want. All right, so if you look here first at each hydrogen, okay, each hydrogen here has 2 valence electrons around them. Okay, hydrogen is a weirdo. He only wants 2 valence electrons. So each hydrogen is happy. All right, but then when you look at the nitrogen, okay, look at the number of electrons around the nitrogen. All right, nitrogen just has 6 electrons around him right now. That's not good. Okay, nitrogen wants 8 valence electrons. Typically, most elements want 8 valence electrons to be happy. So you need to make him happy. You give him 2 more valence electrons here. Okay, you just literally draw them kind of on an empty side here of the nitrogen. Now, if you look, nitrogen has 8 valence electrons around him, right? So now that every element in our picture is happy, you always check that, make sure every element is happy, total them up. See if they match that magic number that we said we needed here from step 1. So if I count up the electrons, there are 8. That is the number we said that we needed, all right? So we are done. This is the dot structure for NH3. And if you look, you can check here with honk, okay? Honk 1, 2, 3, 4, all right, tells us, all right, that nitrogen wants 3 bonds. And if you look closely here at the picture, nitrogen has 1, 2, 3 bonds. It also tells us each hydrogen wants 1 bond. So every hydrogen here has just 1 bond. Okay, so it actually does work according to Hunk as well. All right, so you need to follow your steps. Eventually, you got to get to a point where you know those steps and you can do the dot structures here. All right, so now we're going to do another example here. We're going to do the dot structure for water, but we're going to follow the exact same steps. So first step is we're going to total up our valence electrons available for the molecule. So we'll do this with each individual element. So hydrogen has 1 valence electron, okay, but there are 2 hydrogens in the formula. Okay, so 1 times 2. Each hydrogen is bringing in 1. There are 2 total in the formula. Plus, all right, oxygen has 6 valence electrons times there's just 1 oxygen in our formula. So when we total this up, it is 8. Okay, again, don't think that it has to be 8 or a multiple of 8. It just so happens that these first 2 examples we did were both 8. All right, so then we keep following our steps. It says any carbons or nitrogens in the center. Well, in H2O, there are no carbons or nitrogens. So the rule says whatever there's less of, okay, you put in the center. Okay, so in this case, there's 2 hydrogen, 1 oxygen, so there's less oxygen. The oxygen is going to go in the center. Okay, so the next part says whatever's left goes around your center. All right, well, there's still 2 hydrogens in my formula, so we try to put them as evenly as possible. I'm going to put 1 on each side of my oxygen. All right, whoever you put next to your center has to share at least a pair with the center. Okay, and people always say, well, how do I know if it's going to be a single bond or a double bond? Trust me, as you work through the steps and you work through examples, you'll see. All right, you can figure out if it's going to be single bond or double bond. Okay, just we're not there yet. All right, so whoever's next to the center has to share at least a pair with the center. And then don't forget this step, make everybody happy. All right, so if we look at our picture here, each hydrogen has 2 electrons around it. So each hydrogen is happy. Hydrogen wants 2. But if you look at oxygen, oxygen only has 4 around him. All right. Oxygen wants 8 valence electrons. So you have to add extra electrons on him. All right. So he needs 4 more total electrons. So when I draw in these 4, now oxygen is happy. People say, well, oh, what if the numbers don't work? Well, the rule says you have to make everybody happy. All right. So that's what we did here. All right, now we're ready to total up our electrons. If we count 2, 4, 6, 8, that matches our total that we totaled up. All right, everybody's happy. We hit our magic number. So this is the structure for water. And it does work according to Hunk as well. All right, so now we're going to try an example that's a little bit more fun. So we're going to do CO2 here, but we're going to follow the exact same steps. All right, so the first element we see is carbon. When you look up carbon on the table, carbon has 4 valence electrons. Okay, so how many carbons are in the formula? CO2, there's just 1, so it's 4 times 1. Okay, plus how many valence electrons for each oxygen? It's in the 6A, so there's 6. All right, but then there's 2 oxygens in the formula. All right, so when we total up this one here, we got 12 plus 4 is going to be 16. Okay, so we have 16 electrons that must be in this picture. So that means when this is done, yes, you're going to have 16 dots, all right, that have to be there or it's wrong. Any more, any less than 16, you're wrong. All right, so then the next step says you put any carbons or nitrogens in the center. So in this formula, there's 1 carbon, so that's going to go in the center. All right, whatever's left goes around it, and you try to put it as evenly as possible. So there's 2 oxygens. So I'm going to put 1 on each side here. Okay, whoever you put next to the center has to share at least a pair with the center. Again, if you're wrong, you'll figure this out very quickly. All right, so you have to share at least a pair. All right, and then you make everybody happy. All right, so if you look at this picture, carbon in the center just has 4 electrons around him. Carbon wants 8 valence electrons. So you just add in 4 more to the carbon. 2 on top, 2 on the bottom. These electrons are typically in pairs here. All right. Check the oxygens now. You have to make them happy. Each oxygen only has 2 electrons around it. So each oxygen is going to need 6 more electrons here, or 3 more pairs each. Again, what if I'm wrong? Doesn't matter. The rule says make everybody happy. Okay, so you had to make everybody happy in your picture. Now you go back and total up. Okay, so when you do this here, you'll quickly realize that you're over. If you total up your electrons, you're at 20. All right, so if you remember back to the steps, it says if you're over, you're going to need to add double or triple bonds. Okay, so in this case, we're over by 2 pairs. So that means we're either going to have to add in a triple bond, because that would be 2 more bonds, or we're going to have to add in 2 double bonds to get those 2 bonds. So people always say, well, how do I know what it is? Well, this is an example of where hunk is actually helpful here. All right, hunk 1, 2, 3, 4 says oxygen likes 2 bonds. Okay, so it makes sense that each oxygen here is going to want 2 bonds. So instead of doing a triple bond, I'm just going to do a double bond between each. Okay, so what you do is you go back here and you add your double bond. So I'll pick this first one here. I'm just going to add in another pair of electrons between the carbon and the oxygen. All right, but when you do that, you have to eliminate a pair from each. Okay, if you don't eliminate a pair of electrons from each, you would now have more electrons, and you would have atoms here that have more than 8 valence electrons. So once I add in that shared pair, I have to eliminate a pair of electrons from the oxygen and a pair of electrons from the carbon. Okay, you have to eliminate a pair of electrons from each of the participants in the double bond. Okay, so then I add the other double bond between this carbon and oxygen, but same deal. Once you do that, okay, you have to eliminate a pair of electrons between each of the participants. So carbon loses, and then oxygen loses. It doesn't matter which ones you pull off of the oxygen here, all right? But you have to remove a pair from each of the participants in the double bond, or you would be over the number of valence electrons, okay? So when we look at this here, all right, now when you total this up, all right, you are at 16. All right, so you now hit your magic number of 16 valence electrons. And if you check, oxygen has 8 around him, this oxygen has 8, and carbon has 8 as well. Carbon even works with hunk. Okay, so if you look at hunk 1, 2, 3, 4, it says that carbon likes 4 bonds. Essentially, carbon has 4 bonds. There's 2 bonds here and 2 bonds here, which makes 4. All right, so you have to pay attention to your steps. And if you ever total up your valence electrons and you're over, all right, you have to add in double or triple bonds until you make it work. But you have to remember to eliminate a pair from each of your participants, all right, in your double bond. So now we're going to try another example here. We're going to do this for N2. We're going to follow all the steps. So first thing we do is figure out how many valence electrons there are total here available. So when I look up nitrogen on the periodic table, there are 5 valence electrons for nitrogen, but then there are 2 nitrogens in this formula. So 5 times 2 means we have 10 total electrons that need to be in our picture. Any more, any less than 10, we know we're wrong. Okay, so when we follow our steps, all right, we put any carbons or nitrogens in the center. Well, essentially for this molecule, it's a diatomic, we have both elements being nitrogen. So we kind of put them side by side. Essentially, both are acting as our quote unquote center. All right, so if you keep following your steps, says whoever's next to each other has to share at least a pair. So if these guys are your center, they're next to each other, they have to share at least a pair of electrons. Okay, so then make everybody happy. All right, so each nitrogen right now only has 2. Nitrogen wants 8 valence electrons, so I need to add 3 more pairs, 6 more electrons to each nitrogen. Again, what if I'm wrong? Don't worry about it. You'll figure it out here in a second. So I made everybody happy. The rule says you have to make everybody happy. But when I total up my valence electrons here, I can quickly see that I'm over. I'm at 14 electrons. All right, I can only have 10. So that means I'm over by 2 pairs of electrons. So the only thing I can do to get 2 more bonds here in this is to add a triple bond. All right, so when I add in the first extra bond between the center here, all right, I have to remember that you have to eliminate a pair of electrons from each of your participants in your now double bond. So each nitrogen was participating, so we have to remove a pair from each. Again, it doesn't really matter which pair you remove, but again, you're still not at the number you need, so you have to add in another bond, essentially making this a triple bond. But same thing, once you add in your extra bond, you need to eliminate here a pair from each. So this end loses a pair, and this end loses a pair. All right, so now when you total this up here, all right, you're at 10 total electrons in your picture. All right, and if you check each nitrogen has 8 valence electrons around each. Okay, so this would be the correct dot structure here for N2. All right, and if you check it according to Honk says nitrogen likes 3 bonds. It has 3 bonds there between it. It's a triple bond. So we're going to do one more example here. We're going to do the dot structure for propene. All right, so if you remember back to naming rules here, anytime you see something with like an "ene" ending, that's going to mean it's an alkene. So we know it's going to have the elements C and H in it. The prefix prop, all right, here tells us that there's going to be 3 carbons. And because it's an "ene", that means it's going to be just times 2 then for the number of hydrogens. So it's going to be C3H6. So that's the formula we're using here, but we're going to follow our steps. First thing we do is we total up the number of valence electrons we have available here for the molecule. So the first element we have is carbon. So each carbon has 4 valence electrons, all right, but there are 3 carbons in the formula C3H6, all right. And then the next element we see is hydrogen. Each hydrogen has 1 valence electron, all right. There are 6 hydrogens in your formula. So when we total this up, we get 12 plus 6. That means we have 18 valence electrons that need to be in our picture. Okay, any more or less, we're wrong. Okay, so if you follow your steps now, it says you put any carbons or nitrogens in the center. Well, I do have carbons. I have 3 carbons here. So essentially, the 3 carbons are going to act like your quote unquote center. All right, so you put the 3 carbons kind of next to each other here. This is going to be your center of your molecule. All right, since they're next to each other here in the center, they have to share at least a pair. Okay, then it says whoever's left has to go around your center, and you want to put them as evenly as possible. So I have 6 hydrogens left. Okay, so it would make sense here that I would put kind of one on top of each carbon and one on the bottom of each carbon. Okay, that would split them up as evenly as possible, and I'm still putting my hydrogens around the center. That would be 6 hydrogens. Whoever's next to your center has to share at least a pair with the center. So each of these hydrogens was next to the carbon in the center, so they will share a pair with the center. Be careful here. People always make the mistake. They start sharing pairs between these hydrogens. Well, the rule says whoever is next to the center shares with the center. Okay, they're not going to share with each other here. All right, so be very careful with that. All right, so now we put our atoms that were left here around it. So the next step says make everybody happy. If you look, each hydrogen has 2. Okay, so each hydrogen is happy. Carbon wants 8 valence electrons. So if you notice here, the carbon in the center is good. He has 8 electrons around him, but the carbons on the ends only have 6. So each of those carbons needs an extra pair of electrons. All right, so I made everybody happy. Now I total up. Okay, you always make them happy and then total up. So when I do this, I can quickly see here that I'm over. Okay, I'm going to be at 20 electrons when you count up all your dots. All right, I can only have 18. So I'm over by 1 pair. That means there needs to be a double bond somewhere. So the question is, okay, where can I put that? All right, so first, you know there cannot be a double bond with a hydrogen because hydrogen only wants 1 bond, okay? 2 total valence electrons or 1 bond. So it's going to have to be between the carbons, all right? So then something interesting is going to happen here. So when I'll just pick 2 of the carbons here. If I put the double bond here, all right, when you add in your double bond, the rule says you have to eliminate a pair from each of the participants, okay, in your double bond. All right, so I have to eliminate this pair of electrons from that carbon. But then when I go to the other carbon, okay, there's no pairs of electrons to eliminate. All right, so you have to realize here that if you left it like this, first of all, it's wrong, not to mention the center carbon would have 10 electrons around him. He only wants 8. All right, you have to quickly realize here that You can solve this problem by getting rid of one of the hydrogens here on that carbon and put the hydrogen with the end carbon. Okay, that solves your problem now. Now, if you total up your valence electrons, you would be at 18 dots. Everybody in your picture here is happy. All right, not to mention this fulfills Honk. Honk says carbon likes 4 bonds. All right, that carbon with the lone pair of electrons is not a bond. So you typically hardly ever see carbon with lone pairs. It can happen, but it's not really usually going to happen. So this is the only way this structure would work. With everything great in chemistry, there are some exceptions here to this octet rule, to the fact that some elements, don't want that magic number of 8. So the first one here, we use it all the time, so it doesn't even really seem like an exception, but hydrogen only wants 2 valence electrons here in these dot structures. So you would never give him more than 2. If you draw a picture and your hydrogen has more than 2 dots around it, you know you're wrong. All right. So some other exceptions here. Boron is typically satisfied with just 6 valence electrons. This is just something you have to watch out for. And beryllium is happy with 4. So the way to remember this is just boron and beryllium will never double bond. When you're doing your dot structures here involving boron and beryllium, usually the only way they would work is if you had double bonds with those guys. So you just got to remember they don't double bond, they just take less. And it's just something you got to practice. Nitrogen can be satisfied with 7 valence electrons. It's very rare. We might not see an example with this at all, but it can happen. If you total up your valence electrons, you're like, whoa, it's an odd number. It's probably because nitrogen's doing something weird. And then there are a few elements here, and there's even more than this. Okay, so arsenic, sulfur, iodine, selenium, phosphorus, they can take more than 8. Okay, and people always say, well, how would I know? All right, if you follow your rules, okay, like so for example here, if you look at this SCl6, all right, you can say, wow, that looks crazy. But if you follow your rules, it says whatever atom there's less of, you put in the center, and whatever's left goes around it. So the 6 chlorine that are remaining would have no choice but to go around your sulfur, right? And if you have to share a pair with the center, okay, the only way that would work is if that center element can expand and just take more. So if you follow your rules, these things kind of just fall into place. But these are exceptions that can happen. So I just wanted to point out here what structural formulas are. Um, Typically, I'm going to ask you to draw the dot structures, so you have to show all the dots, okay? But a structural formula is when you remove any of the shared pairs and you just replace them with a line, okay? So this would be a structural formula here for water. Notice you still see the unshared pairs of electrons there on the oxygen, but the electrons that were involved in the bonds between the oxygen and the hydrogen get replaced with a line. Okay, so sometimes these are just if you're doing something and you want to quick do it, you can do a structural formula. But typically, I'm going to ask you to do a dot structure. And I just wanted you to see what this would look like if it was like a triple bond. So something like nitrogen here has the triple bond, and you can see there what that would look like in a structural formula. So again, you just remove the shared pairs and you put in lines or dashes to represent the bond. That's a structural formula. The last thing I'm going to talk about here is something called resonance structures. This is just when there's more than one possible correct way to draw a dot structure for a substance. All right, so you could do it in more than one way and still be correct. It's found in a lot of double bonded molecules. All right, so don't think every double bonded molecule has resonance, but it's found in a lot of molecules that do have double bonds. So for example here, this example is showing you the resonance structures that exist for the carbonate ion. So if you look down here, they're not showing you all of the extra, dots here. They're just showing you how this would kind of be arranged. So if you were to do the dot structure here for the carbonate ion, you'd have your carbon in the center, and it would be attached to your 3 oxygens. Okay, but one of the oxygens would have a double bond, and the other 2 would have a single bond. All right, so what's really different if this carbon and oxygen had the double bond, or if this carbon and oxygen has the double bond? There is no difference. It's the same exact dot structure. So we said that that is resonance. Typically, when you're drawing these resonance structures, you have to show the double arrow here because that's indicating that all three of these structures are possible. And you would put them in brackets if they have a charge with the charge outside. All right, so this would be in brackets here, and the 2 minus would be outside of it. But this is just showing you that there's more than one way to draw this dot structure correctly. This is a more complicated example. This is an organic chemistry example. This structure here is benzene, okay? But it's showing you here with this double arrow that there's more than one way to draw this correctly. You can see there's double bonds here between, all right? And you don't need to know what these symbols mean. I'm not going to ask you anything about that. But you can see these double bonds here. They can switch and they can kind of move and form between different carbons. So we say that that has resonance. So typically they draw it like this. That's something you might see if you take organic chemistry, but I just want you to see another example of how a structure can have more than one way to draw it correctly.